Hello, welcome to section 4.1. This is the beginning of our trigonometry journey. Chapter 4, Chapter 5, Chapter 6 deal in trigonometry. So let's go ahead and get started. You've worked with degrees for measuring angles. Also, there are radian measures for angles. Some of you have worked with them, some perhaps not. We're interested in talking about radian measures for angles oftentimes when we're interested in a portion of the circumference. So sometimes in a circle we're just, as we're rotating around a circle, we're only interested in the angle measure, but sometimes it's also tied into an arc length as well. And a radian is tied in tightly with an arc length, as you can see. So what is a radian? A radian is a measure of an angle. Now, it's deals with the arc length, but it's not the measure of the arc length. It's the measure. It's an angle measure. It's like measuring in degrees. It's just a different unit measure. But it's the measure of an angle, the angle that intercepts, and you might want to think of that as snow cones. Here's an angle that snow cones this arc. It intercepts it here and here. It intercepts an arc, we'll call it S, that is the equal distance to the radius. So this distance would be equal to this, makes this be 1 radian. Anything bigger than that is going to be bigger than 1 radian. Anything smaller is going to be that fractional smaller than that. And therefore, this means that theta is equal to the arc length divided by r. And later on, you're going to see another formula based on those things, but it is the same formula. Everything, if you look back at this, and if I happen to take the above equation from our definition of a radian and solve for S, this thing becomes S equals multiply both sides by R times theta, or theta times R. So really just one formula, but we'll talk about arc length just a little bit and why this one should make some sense to us. Worth noting that 1 radian, or excuse me, 1 pi radians, 3.14, etc. radians equals 180 degrees, and there's our conversion. And we'll often talk about that being pi on 180 degrees is 1, and so is 180 degrees on pi radians. Both of those are 1, and we'll use those for conversions, and that's discussed right through here. It talks about converting from degrees to radians, and this should make some sense. If I've got a degree measure, say I've got 60 degrees, and I want to cancel degrees, then I need degrees in the denominator, 180 degrees, so the degrees unit cancels and leaves me with a radian measure. If you've taken chemistry, you do that kind of stuff in chemistry, I believe, all the time, where you make sure you cancel the units. If we want to cancel radians, then of course, if we have a radian measure, then of course we divide by pi radians to cancel the unit measure, radians. To apply these two conversion rules, use basic relations. Pi radians is 180 degrees. Okay, for a circle of radius r, a central angle theta intercepts an arc length is given by this. Well, I guess I understand that if I understand this, but let's talk about that for a minute. Here we've got a circle, obviously, and let's just say we have from the center of that circle, let's say we're interested in finding the measure of this arc right here. And let's say the radian measure is 5. So how would we define this arc in terms of parts of the circle? This arc is part of the circumference. It's just a fraction of the circumference. Let's say this is theta right in here. So let's say this distance arc, well, we'll come back to that. Let's just call this r for right now. So we're a fraction of the entire circumference. Well, what's our formula for circumference? Circumference, as we all know, is 2 pi r, or as we all should know, is circumference equals 2 pi r. The arc length is just a fraction of 2 pi r. What fraction are we dealing with here? Theta out of the full revolution. So we're dealing with theta degrees out of 360 degrees, but let's go to radian land with that. We talked about pi radians is 180 degrees, so 2 pi gets us all the way around the circle. We only went around S. So this is S divided by 2 pi. In this case, maybe we'd have a radius of 1. So S equals, let's see, I'm sorry, not S, theta. Theta, we went theta out of that 2 pi rotation right here. Okay, now if I do that, I've got to cancel here, or I may cancel here, and I have S equals theta times R. And there we have it. There's our formula. And so it's one that we should ultimately understand if we know that circumference is 2 pi r. We're just a fraction of that. So an arc length is a fraction of 2 pi r. What fraction? The angle measure divided by the full revolution that we need. And of course the 2 pi's cancel, and there we have it. Okay, linear speed. Any speeds are going to be distance traveled divided by time, like miles per hour, feet per second, things along that line. So a linear speed as we travel around a circle, our linear speed, say I go from this point to this point, let's say this is a distance of 5 and I do it in 2 seconds. Say this is 5 feet, we do it in seconds, it's just 5 divided by 2 feet per second. So this ought to make sense. It's our length divided by time. And the speed of the central angle, like this central angle, is how much did the central angle change? So what is the measure of theta divided by time? Those should make some sense as well, I believe. Okay. Then we are to estimate the angle to the nearest 1/2 radian. All right, so we're going to remember that, let's see, get my trusty ruler here. We're going to remember that pi radians would get us from, we always start our revolutions in trig from this. This would be 0 degrees or 0 radians, and then we just start opening up an angle counterclockwise, and this would get us around a pi, or approximately 3.14. So it's probably, we wouldn't have to memorize this, but you may do it so often that you just naturally memorize it. But 3.14 divided by 2 is 1.57. So this is 1.57 approximately radians to here, 3.14 to there. 1.57 plus 3.14 would rotate us all the way around to here to 4.71, and this is 6.28-ish. Again, all of these are approximations because pi is an irrational number. So we take this angle 12, this angle from 12, I'm just going to try to ballpark it in here, and it looks like maybe about like this. Pretty good representation. I'm going to just cheat and cover it up here. Oh, that was really good. I can see through my paper here. And we're about right in there, and we are looking for this angle measures. We actually rotate backwards. So as we rotate backwards, we would call that a negative angle. And I needed to go negative 3.14 just to get here. Each quadrant's 1.57. So if it's 1.57, you can almost get away with this. There's 0.5, and there's 1, and it's almost, when you go by thirds, it's almost a half a radian. When we divide a quadrant by thirds, it's about a half, and we're just ballparking this. So we get 3, plus this would be about another half and another quarter. So we're 3.67-ish plus another quarter. We're definitely getting close to being 4 at that point. Again, remember, it's 4.71 around to here. If I go back about 0.5, third of a radian from 4.7. I'm about 4.2. We're definitely in the ballpark of 4, but it's negative, so we would just go, maybe I'll put theta in here. So theta is approximately -4 radians. That's to the nearest half. I'm pretty confident with that. Okay, in 13 through 18, determine the quadrant in which the angle lies. The quadrant in which the angle lies is a lot clearer. It's not an estimation. We're not just ballparking things like 12. We should be able to tell that. So I didn't leave a little place for you to draw this angle. 5/6 pi. Well, if we rotate it around to here, this would be 6/6 pi, a full pi. So 5/6 would be 1/6, 2/6, 3/6. 4/6, 5/6 pi would be this angle. And where does it terminate? Determine the quadrant in which the angle lies. The angle's given measure ends up terminating in quadrant 2. So get good at this. A third of, they give us a fraction. I'd rather have that. I'd rather have fractions of pi than these. Fractions of pi, we're going backwards. 3/3 would get me to here. So it's like 1/3, 2/3, 3/3, 4/3, 5/3. Notice if I went one more third, 6/3 would get us to there. So determine the quadrant in which each angle lies, the angle measure. So we rotate around to here, and we end up being this angle, and it terminates in quadrant 1. Now 3.5, careful. The common mistake is we get so used to seeing pi, we think 1 pi, 2 pi, 3 pi, 3.5 pi. We'd be down here, but 3.5. That's just a number. It's radians still. It's not a degree measure, but this is 3.14. 3.14 gets us to here. There's only a little bit left, and not enough to get us to that, if you recall, 4.71. So we're somewhere in here, quadrant 3. And likewise, 2.25. This is 1.57, 3.14 divided by 2. Here's 3.14, 2.25 stops somewhere in quadrant 2. Okay. So, sketch each angle in standard position. We want to get really good at this when we have a fraction. It takes 4/4 to get around to here. This is 4/4 pi. So it would be 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4. We want to be at 3/4. So our angle measure is right here, and let's indicate that with an arc and a direction that we're going. 4/3 pi. Well, this would be 3/3 pi over here. So about be 60 degrees, wouldn't it? 1/3, 2/3, 3/3, 4/3, 5/3, 6/3. We should get pretty good at that. 4/3 would get me to 1, 2, 3, 4/3 pi right here. Which way is the angle rotation? Well, it's positive, so we're talking about that angle. 11/6. 180 degrees is pi divided by 6. That's 30 degrees. So every 30 degrees I want a tick mark. 1/6, 2/6, there we go. 3/6, 4/6, 5/6, 6/6, 7, 8, 9/6, 10, 11/6. And it's tempting to say that our angle's right here. But our angle was 11/6 pi. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We went around this way. And now we're -2/3. So if I split my graph in thirds, 1/3, 2/3, 3/3, 4/3, 5/3, 6/3, we're going around backwards, so clockwise from 0, 1/3, 2/3. Our angle gets us to there. We rotated that way. Now 2, we're just going to ballpark this one. Remember, this is 1.57. Here's 3.14. So we're about 0.4 away from here, and 2 is about 1 point. We're definitely closer to here, so I'm just going to say somewhere about in there is our rotation. And that angle measure is 2. And then negative 3 pi. Well, I'm just going to start my negative rotation. That's negative 1, negative 2 pi's, negative 3 pi's. So we do end up here. And our rotation would look, I'm just going to spiral it. We went negative 1 pi, 2 pi, 3 pi. So the reader should be able to determine that that isn't just pi or negative pi. It's negative 1, 2, 3 pi. All right, determine 2 coterminal. Terminal means stopping point. Coterminal, 2 that stop in the same place. 2 coterminal angles in radian measure, 1 positive and 1 negative for each angle. So we have an angle of 7/6 pi. How else could we get there? I could go backwards by sixths. It would be 30 degrees, so 1 6, 2 6, 3 6, 4 6, 5 6, 6 6. So I could say theta is negative 1, 2, 3, 4, 5. That's the most obvious. And then for the others, we need 1 positive, 1 negative. I've got a negative. Then we have to do multiple revolutions. So to get here in positive manner, I could go here and then spin a full another 2 pi around. So my other one would be, let's spin around to 7/6 pi, but let's add 2 pi to that, or 12/6 pi, and we end up at 19/6 pi. And B, virtually the same problem. Fourths, 1/4, 2/4, 3/4. Theta could be negative 3/4 pi. There's our negative solution. Or theta could be 5/4 pi plus spin a full revolution around, 2 pi more, or 8/4 pi, and we get 13/4 pi. Note they say many correct answers. Oh yeah, we could come here and spin around 15 times if we wanted to. But these would be the most likely choices for just taking one additional revolution. Okay, negative 7/8. That means I need 8 tick marks from here to here. So 4 from here to here. So I'm going to divide it in half and half again. 1, 2, 3, 4. Divide it in half and half again. 1, 2, 3, 4, 5, 6, 7. So here's where we are right now. You might not need to draw that, but I think it's probably not a bad idea. So there's our negative 7/8 pi. We could go around this way. That would be 8/8, 9/8 pi. So if we call it theta, theta could equal 9/8 pi. It gets us to the same place. Or I need a negative here. I could say let's go negative 7/8 pi, and let's just keep going around. So minus another revolution, 2 pi. Or 16/8 pi gives me negative 23/8 pi. Pi on 12, let's see, that means it's 12 of those units to get around here, 6 to here, so if I cut it in half, and then I need 3 steps to get here, there's 1, 2, 3, 4, 5, 6, but I'm just at pi on 12. If you're curious, 180 degrees divided by 12, that's 15 degrees. So we're in the ballpark here. Okay, so I could go backwards. If I went backwards all the way to here, that would be negative 2 pi or negative 24/12, but I only want to go one short of that. So theta could be negative 23/12 pi. It'd be 12 to here, 6 more to there, 18, 19, 20, 21, 22, 23. Okay. Or theta, we could just take the easy route and just go forward 1/12 pi. 1/12 pi or pi on 12. Okay, now, an area we may be more comfortable with is once we get to degrees. 87.9 degrees rotated from here is going to be close to 90, but shy of 90. Determine the quadrant in which the angle lies, where it terminates is what they mean. So here's our angle, and that is in quadrant 1. Negative 8.5 degrees goes backwards, but not very far at all, and leaves us in quadrant 4. Negative 245, negative 90, negative 180, negative 270. So we're somewhere in here. Don't need to be precise, we just need to know that we land in quadrant 3. And just 12 little degrees doesn't get me close to 90. We're somewhere over in here in quadrant 1. Very simple for us, I believe. Determine two coterminal angles in degree measure that get us to here, one positive, one negative. So for my positive, I could go 114 degrees and just continue on another 360. And we get what? 474 degrees. Or I could spin 114 and then go backwards 360. 114 degrees. Go backwards to get there. Or go backwards 360 and then 114 and we terminate at the same place. Either way, minus 360. And what do we get there? 246 degrees. Now here they've already taken us more than 360 degrees backwards. So I'm 360 and it looks like another 30 in here to get to 390. So I could just say, how about we just go the easy route and just say theta is negative 30 degrees. Gets us to the same spot. Just go negative 30 and forget about that extra spin. Or we could spin around this way, which would be, to get to here would be like spinning around 360 and coming back 30. So I could say theta is 360 degrees minus 30 gets us to the same spot, or 330 degrees. So 445, let's do this without a diagram. 445, hopefully we notice that's more than a full revolution. So I could subtract a revolution from that. And what do we get here? 445 minus 360, we get 85 degrees. And then that's our positive answer. Let's get a negative one. Well, let's just spin around backwards again. Let's take 85 degrees minus another 360 degrees, and we get negative 275 degrees. Okay, theta. That's backwards revolutions, more than one, in fact, more than two. I think I will draw a quick diagram of this one. This would be negative 360, negative 720, and then we're left with another 20 to get to there. So theta could just be negative 20 degrees. It also could be negative 360 and 20. Could have negative 380 here. And to rotate this way, we could go 360 minus 20. Go backwards beyond it and then come back. 360 degrees minus 20 degrees, 340 degrees. Okay, at this point right now, I'm going to stop this. There'll be a part 2 to this. We still have a couple pages. I don't think there's anything particularly troubling on it, but good time to take a break. So stay tuned.